using the normal distribution to approximate other distributions. On January the 8th, 2003, an Air Midwest Beechcraft operating out of Charlotte, North Carolina, crashed, killing all 21 people on board. Although pilots had totaled up the takeoff weight of the aircraft before the flight, and it was within limits, the plane was actually overloaded and out of balance because of incorrect Federal Aviation approved passenger weight estimates. It turned out that both the average weight of passengers and the weight of the baggage exceeded the estimated quantity, in the case of passengers by a total of 20 pounds per passenger. So the aircraft was 580 pounds above its maximum allowable takeoff weight. This is simply to say that the weight of passengers on an airline is critically important to the safety of that airline. And a naive calculation which assumes the same weight for all men and another for all women and a constant weight for each bag is perhaps a little too naive given the gravity of the issue. Of course, one possible response is to weigh passengers, which is now done by Samoan Airlines, or obtain a more careful estimate of the total passenger weight on an aircraft. The actual distribution of total passenger weight is very complex. Assuming I have 200 passengers, the weight of each is a random quantity. And when you add up 200 random variables, typically you end up with a rather complicated distribution. Fortunately, it can be fairly accurately and easily approximated. Assume, for example, that the weight of men, I'm calling this xi, are independent random variables with expected value 190 pounds and with variance 30 squared, the standard deviation 30. Similarly, assume that the weight of women, yi, have expected value 160 and standard deviation 25. Let's suppose that there are 100 men and 100 women on a given plane. What's the probability under these circumstances that the total weight of all of the passengers, I'll call that W, that's the sum of 100 independent values of x, the sum of xi, plus the sum of 100 values of yi. What's the probability that that weight, total weight, exceeds some threshold or critical value of 36,000 pounds? We can solve this problem if we assume that weights are normally distributed. Let's assume that W, therefore, has a normal distribution. We can compute its expected value. It consists of 100 men with average weight 190, plus 100 women, average weight 160. That works out to 35,000 pounds. And assuming that the passengers are all independent random variables, then the variance is 100 times 30 squared, that's the variance of a man, plus 100 times 25 squared, the variance of a woman, and that turns out to be 152,500. The rest of this calculation is quite routine. For a normal random variable, the probability W is bigger than 36,000 is the probability that W minus 35,000 over the square root of its variance exceeds 36,000 minus 35,000, again over the square root of its variance, which turns out to be the probability that a standard normal random variable Z is bigger than 2.56 or so. That's 0.0052. That value determined from a normal table. While this number might appear to be relatively small, given the ramifications of an overloaded aircraft, surely it's still too large. In the first place, if our assumptions fail, the number may exceed this. In the second place, even if that number were accurate, this would mean one plane out of every 200, roughly, flies overloaded. So, evidently, we should either change the type of aircraft or reduce the load on it. The central limit theorem. The central limit theorem concerns sums of random variables. Let's start with the sum of the numbers obtained on a fair die. In general, what the central limit theorem does is gives us a justification for using a normal distribution when we're dealing with linear combinations of random variables which have non-normal distributions. So let's begin with a fair die, and suppose that we define Sn to be the sum of the outcomes when we throw a die n times. For example, if n is equal to 1, we have one throw of the die, the outcomes are 1 up to 6, the probabilities of those outcomes all 1/6, and we've plotted below the probability histogram of that distribution. Clearly uniform. What if we throw 2 dice? The values that we obtain as sums run between 2 and 12. The probabilities run from 1 over 36 at 2 up to a maximum of 6 over 36, and then back down again to 1 over 36 at 12. And the graph represents of the histogram is a triangular-looking object. What difference does it make to this shape if now we throw 3 dice and add the outcomes? Of course, now the outcomes run from 3 up to 18, with probabilities beginning at 1 over 6 cubed. What's important in the probability histogram graph below is that they now begin to resemble a bell-shaped histogram, a bell-shaped curve, if you wish. More and more, evidently, like the normal shape. This is no accident. When we add n independent random variables, although individually they are non-normal, the sum appears to become more and more normally distributed as n increases. This is a consequence of one of the most famous theorems in probability and statistics, the central limit theorem. As we add more and more independent random variables, we have a distribution which approaches a normal distribution. More specifically, the central limit theorem says that if we have independent random variables, x1, x2, up to xn, all drawn from the same distribution, so therefore with the same mean, we call it mu, and variance sigma squared, then for large values of n, the approximate distribution of the sum of xi, I goes from 1 up to n, is normal, with mean n times mu, and with variance n times sigma squared. There's one problem with this statement, and that is the target, the thing we're approaching, that normal distribution, is itself moving as n changes, because its mean, n mu, and its variance, n sigma squared, are growing and going to infinity, in fact, as n goes to infinity. So to make this statement a little bit more precise, we need a target that stays in one place. So the formal definition of the central limit theorem is the following. I have x1 up to xn independent random variables. Again, they all have the same distribution with mean mu and variance sigma squared. And as n goes to infinity, we take the partial sum, the sum of xi, I goes from 1 up to n, and we subtract off the mean of that sum, n times mu, and we divide by its standard deviation, sigma, times the square root of n. So now we have a standardized random variable with expected value 0 and with variance 1. The central limit theorem says that that random variable approaches a standard normal distribution, normal 0, 1. Indeed, it approaches in the sense that the cumulative distribution function of that standardized random variable approaches the normal 0, 1 cumulative distribution function. It's actually quite easy to show that the sum of xi minus n mu over sigma divided by the square root of n is identical to x bar, the sample mean minus mu, divided by its standard deviation, sigma over the square root of n. And so that's another sequence of random variables which again have a cumulative distribution function approaching the standard normal CDF. Like many theorems in mathematics, the central limit theorem is about limits. We apply it, however, when n is finite in statistics, but large. And what it tells us is that when n is reasonably large, we can approximate the distribution of that partial sum, I goes from 1 up to n of xi, by a normal distribution, of course with appropriate mean and variance. The central limit theorem holds for all distributions for xi, except when xi fails to have a finite variance. That, of course, is rather rare in statistics, and we'll use the central limit theorem to approximate the otherwise very complicated distribution of partial sums or averages x bar. Of course, the accuracy of the normal approximation is better if n is large, but it does depend on the actual distribution of the constituent random variables xi. For example, if xi takes potentially very, very large values with extremely small probability, then the central limit theorem may hold, but it may only hold for extremely large values of n. We've already seen a result which looks very similar on the surface to the central limit theorem. It concerns normally distributed random variables. We know that if x1, x2, xn are independent and each normally distributed with mean mu and variance sigma squared, then the sum of xi, I goes from 1 up to n, is also normal, with mean n mu and variance n sigma squared. When we start with normal, then the sums are themselves always normal for any value of n. When we start with a distribution other than normal, then the sums approach a normal distribution as n increases. Let's return to the airline safety problem. Again, we're going to assume that the weight of men are independent random variables. They have expected value 190 and variance 30 squared. Again, we assume that the weight of women, yi, are independent random variables with the expected value 160 and with variance 25 squared. And again, assume there are 100 men and 100 women on a plane. What's the probability that the total passenger weight W exceeds 36,000 pounds? Well, essentially, we've solved this problem, but we assumed that the total weight W was normally distributed. The question now is, what justification do we have for that statement? Notice that the sum of xi, I goes from 1 up to 100, is the sum of 100 independent random variables, all with a given mean and variance. The central limit theorem, therefore, implies that that sum is approximately normal, with mean n times mu, 100 times 190, and with variance n times sigma squared, 100 times 30 squared. And similarly, the sum of yi, the sum of the weights of the women, is approximately normally distributed with mean 100 times 160 and with variance 100 times 25 squared. Now we're assuming that all of the x's are independent of the y's, that all of the random variables are independent of one another. And since that's the case, then the total weight is the sum of the x's plus the sum of the y's. An approximately normal random variable plus another approximately normal random variable is again roughly normal, and we obtain its mean and variance by simply adding the mean and variances of those two components, giving us W is approximately normally distributed with mean 35,000 and with variance 152,500. And now we carry out exactly the same calculation as before. The probability W is bigger than 36,000 turned out to be something like 0.0052. So the central limit theorem has justified the normality assumption implicit in our previous calculation. But with that in mind, let's look at a few afterthoughts. First, we assumed that the men and women who boarded this plane were all independent draws from a large population of men and a population of women, whose parameters mu and sigma squared we could presumably easily estimate. Are they likely to be genuinely independent of one another? Suppose, for example, M individuals booked together. A husband booked a ticket with his wife, likely to fly together, possibly both above the average weight or potentially below the average weight. Or suppose a professional football team books tickets for 20 individuals to fly to a game. In this case, they're quite likely not to be independent draws from the population of men. Now, of course, in practice, we know how many tickets were booked in pairs or in groups of 15 or 20. We have some information which may allow us to change some of the calculations above, and that might be necessary in the interests of safety.